Hello, my name is Pritesh Rajaguru, and this is Physics 2212, Lab 4, Circuits and Capacitors. So the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel using multimeters to measure the actual values of conventional current and potential differences in each circuit and examine the behavior of ohmic resistors and capacitors. The principles we will be using in this lab are Ohm's law, which is voltage equals to current times resistance, capacitance, which is charge divided by voltage, Node's rule, which is current in equals current out, as energy does not change, and loop rule, which is the total potential difference of our circuit should equal up to be zero. So to construct our first circuit, I will be using Circuit Construction Kit from Colorado PHYS. In this circuit, we're going to be needing two 1.5 volt batteries, a 47 ohm resistor, another 100 ohm resistor, and two ammeters. As you can see to the right, this is the structure of our first circuit, in which the two batteries will be on the left side, the ammeters will be uh, parallel from each other, and then the two resistors should be on the same line. So to your left, you can see the circuit that was created via Colorado FETs. We predicted that the current via Ohm's law would be 0.0204 amps because Ohm's law is voltage divided by resistance, which was 3 volts because of the two 1.5 volt batteries, and then 147 ohms because of the two resistors. The actual current, as you can see via the ammeters on the circuit, is 0.02, so we got fairly close, but theirs wasn't as accurate. If you reverse an ammeter, all that would happen would be that the sign changes. So here we can see the potential difference in our entire circuit. The only major changes we can see is from A to B, which is the two batteries, from C to D, which is our 47 ohm resistor, and E to F. The reason that it's significant here is because we're considering wires and the ammeter as having zero resistance because due to this being an ideal situation. And as we can see here, the circuit starts off with zero and ends with zero. This follows our loop rule, which says that potential difference of our entire circuit should equal up to being zero. So now we'll replace one of the ammeters with a voltmeter. This will tell the voltage throughout the entire circuit. As we can see, the potential difference is 3, as there's no current going throughout the resistors due to the voltmeter having an infinite amount of resistance. So there's no current going through it. This is shown via the ammeter at the bottom. So now we'll put an ammeter in parallel with the 100 ohm resistor. As we can see to the right, the current is the exact same between the two, and the current jumps from 0.02 to 0.06 amps. So this would be the equivalent of just getting rid of the 100 ohm resistor due to the fact that electrons will travel through the path of least resistance, which is through the ammeter, which has zero resistance, while instead of the 100 ohm resistor. So for part 2 of this lab, we're going to be constructing an RC circuit, which you can see to your right. We're going to be needing a 10 ohm light bulb, a 20 ohm light bulb, a 9 volt battery, and a 200 millifaraday capacitor. So when building the RC circuit, we can see that the light bulb does shine for a certain amount of time and then exponentially starts to decrease. This is due to the fact that the capacitors start to charge up, and then once they are fully charged, there is no current going throughout the entire system. The charging time for the capacitors for at least the 10 ohm light bulb was about 9.4 seconds, and the 20 ohm one is about 18.2 seconds. This makes sense because the 20 ohm one is about twice the amount of resistance as the 10 ohm light bulb. When we take the battery out, the discharging time of the capacitors for at least the 10 ohm light bulb was about 12.9 seconds, while the 20 ohm one had about 25.9 seconds. So now we have to find the RC constant, which we can find via the given formula. So to find the RC constant, we have to plot natural log of total voltage divided by initial voltage as a function of time. The slope of this is equal to -1 over RC, which we can find that RC will equal to 6.89 seconds. So now for some discussion questions. What if we did this in real life and we used an actual ammeter instead of an ideal one? Then what would be different between the ideal one and the real one if we had done this? So unlike the online simulation, a real ammeter would have a certain amount of resistance. Um, and because of this, the real circuit would have less current compared to the ideal situation. What if we used a real battery to charge a real capacitor with no resistors in the current? How quickly would our ideal model predict the capacitor to reach a full charge? And what would happen in real life? What would this prediction be in real life? The ideal model would be instantaneous charge of the capacitors as there's no resistance throughout the wires. But this would be impossible in real life as the wires themselves have resistance and so do the other components of the circuit. All right, thank you for your time. I hope you have a wonderful day.